subatomic particles were arranged, and we said that in the nucleus are what? Protons and neutrons. And their similar characteristic is that they both have what? Mass, right? Protons and neutrons have mass. They're found in the nucleus. Come on now. No. Now watch. It'll like... Nope. It was working upstairs. It was working perfectly fine. And now it is. Except that it's really dark. But other than that, it's working perfectly fine. So in the nucleus, we have those protons and neutrons. The electrons, though, we really didn't talk very much about electrons because they have literally no mass. Remember, they're 1/2000th the size of the protons and the neutrons. But it is the electrons that come into play in creating stable compounds. So the compound that we made when we burned magnesium, that magnesium oxide that we produced, that is because of electron interaction. So it is electrons that are responsible for allowing atoms to interact. So electrons, they're like little particles of energy, and I've kind of drawn them so that they look like they're just small little particles, and they're constantly moving. So electrons are constantly moving, and they move in a specific path. So in this one, so you see that one that's close to the nucleus is just going around, 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 much like you think of the moon orbiting the Earth orbiting the sun. Very similar, have very common paths. Remember, electrons are negatively charged, protons are positively charged, so there's an attraction, and that's what helps to hold the electron in its position, because it's attracted to that proton, but its movement keeps it from going in or actually shooting out in any direction. So it keeps it in an orbital path. Electrons would like to get as close to the nucleus as possible, as close to the positive protons as possible, but there's only so much space. So in what they call lower energy levels, those are the energy levels that are closer to the nucleus. The higher the energy level, the faster the electron has to move, the more energy it has to have. And the way to think of this is if you have two electrons, the one that's really close, the one that is out here, they have to make their orbit at the same speed, or not the same speed, but in the same rate. So they've got to be able to do their loop in the same time span. So who has to move faster? The one that's further out. So the purple one has got to make a much further loop at the same time that the inner one can go much slower because it's got a much shorter path to follow. So the further away from the nucleus, the higher the energy level, the higher the energy that electron will have. So electrons are always trying to fill up those that are closest first. So the first energy level, because it's so close to the nucleus, only 2 electrons can fit there. Okay, so when we look at hydrogen, so hydrogen, its little mass, 1.008. So remember that that atomic number tells you that there is 1 proton and 1 electron. As long as you're talking about a neutral atom, remember that that 1 tells you that there's 1 proton, but it also tells you that there's 1 electron. That 1 electron would be in that first energy level because it's going to try to get as close as possible. So what is atomic number 2? Helium. So helium, and it's got its mass as 4.003. So this one, you know, has 2 protons and in a neutral atom, protons and neutrons are the same. 2 protons, 2 neutrons, or 2 electrons. Those 2 electrons fill the first energy level. So when you look at atomic number 3, which is lithium, I don't care. Number 3 tells you 3 protons, 3 electrons. So the atomic number, 3 protons, also tells you numbers of electrons. So can't put any more in the first energy level. So 2 fit in the first energy level. That means that the third electron that lithium has to go into the next level up. So 2 electrons in the first, and it'll have 1 electron in the second. And this continues as you progress across. So beryllium will have how many in the second energy level? 2. Boron will have 3. Carbon then has 4. Nitrogen would have, oxygen, fluorine would be 7. But then we get over to neon. Okay, so if we just continue on, and we get to neon, so neon is 10. It has 2 electrons in the first. It has 8 electrons in the second. 8 electrons, other than hydrogen and helium, 8 electrons is like the magic number. So 8 electrons allows a balanced number of electrons in an energy level. 8 electrons create stability. And so a stable, so this is the full energy level, and that is going to create a very stable atom. So we said helium has 2, but only 2 fit in the first. Neon has 8 in the second, and that makes it stable. So what do you think about argon? It's also going to have 8, okay? So argon's going to have 8. And so this number pattern and part of the reactivity pattern is how they were able to devise the periodic table, because those that are in the same column, at least for the first 2 groups, the first 2 columns and the last 6, their columns indicate the number of electrons that are in the outermost shell. Because all the other shells inside, all the ones that are lower, they're all full. It's the ones that are in the outermost shell, and when you get to 8, that's like that magic number of being stable. They call that the Octet rule, and it really sort of governs what all elements do other than the noble gases. So noble gases are stable because their outer electron shell is full, and so they're not reactive. So they're stable just all by themselves. You can kind of look at it as it looks like this. So if the nucleus is here, the first energy level, it just holds 2. The second energy level, it can hold up to 8. The third energy level, well, it can actually hold up to 18, but 8 is still the most stable, okay? So we still end up with this 8 as a stable number in the outer energy level. Writing, stable number in the outer shell, except for the first 2, hydrogen and helium, because they're so small. 2 is their magic number, but for everything else, it's always going to be 8. So when we looked at magnesium, you had that magnesium metal I sent around. Atomic number is 12. So how many electrons in the first? 2. How many would fit in the second? 8. 8 is the max in the second one. And so that means how many in the third? 2. So this would be in the first, this is in the second, and this is in the third. The first and second energy levels are full. So they're actually pretty stable in magnesium. It's an outer one. It's the outer one that is not 8, the outer one that is reactive. They call that the valence electrons. So the term valence just means outer. Sometimes they just call that the valence number. Even better though, you don't have to memorize these. Because the periodic table, not that one so much, but this periodic table that I give you actually tells you the valence number for the first 2 columns and the last 6. Do you see the number with the capital A at the top? Okay, so hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all of the ones in the first one, they're all 1A. that means they have one electron in their valence shell. So all you have to do is look at the periodic table and look at the top. So you really don't have to know like how many in the first, how many in the second, I don't care. Okay? All you need to do is to be able to pick that out. So everything in the first column, one electron in the outer shell, or its valence number. Second group, which is beryllium, magnesium, calcium, those 2A. They all have 2 electrons in their valence shell, 2 electrons like magnesium in the outer shell. Now, the ones in the middle are a little wonky, so we're going to skip them for a minute, but we will talk about them some. Go all the way over to 3A. You can't see 3A on this one because they didn't put it on that periodic table, but I specifically use this one because it does show you 3A, which is boron and aluminum. So those 2, they have 3 valence electrons. Then carbon and silicon, they would have 4 in their outer shell. And it doesn't matter if it's in the second energy level, third energy level, fourth energy level. It's according to that column. You don't have to be able to figure out which energy level. All you do is look at the number in front of the capital A, and that'll tell you the number of electrons in their outer shell, because those are the ones that are most reactive. If they don't have 8, that's what they want. The goal is always to create this stability of 8, to be able to form a stable interaction with other electrons so that they're not reactive anymore. So you may see them drawn with you see the Roman numeral, so that A tells you, the number in front of the A tells you the valence number, or the valence electrons. They will oftentimes use dots. So Lewis, Dr. Lewis, one that did a lot of work with acids and bases, but also looked at these, he said that you can use a dot to represent the valence electrons. Not all of them, but the electrons in the outer shell. So like with hydrogen, you would just put a single dot. Okay? Same thing with lithium, sodium, and potassium. You would again just put a single dot. So that dot can represent the valence electron. That's the one that's most reactive. Everything in group 2 would have 2 dots. Group 3 would have 3. Now when I have more than 2, I actually spread my dots out, because that way it helps me to try to figure out how I'm going to pair them or how I'm going to swap them. So I would put 3 above to the side and below. You could put it side to side and above, wouldn't matter. Just sort of split them up. Same thing, 1, 2, 3. So with carbon, I put 1 above, 1 below, 1 to the left, 1 to the right. Same thing with silicon, because it's in group 4. Nitrogen then, you run out of top and bottom, left and right, so you have to double up. So nitrogen, you have to pair 1, and then the other ones are singlets because it's 5. Same thing with phosphorus. Oxygen's going to end up with 2 pairs that are already matched, but it'll have 2 single electrons, then make a total of 6. Same thing with sulfur. Well, fluorine and chlorine, though, you're going to put 7. So you're going to put pair off 2 and 2, 2 and 2. There's only 1 single electron on one of the sides. Everything else is already paired. Because the goal is to achieve electron pairs that look like what? The noble gases, which will be 8. And so they will have their complete shell. So that's a stable arrangement. Remember that hydrogen and helium are the oddballs, so they only need 2. But everything else is always going for 8. So that 8 is creating stability. There's 2 different ways you can create stability. You're either going to have atoms with a lot of electrons and atoms with few electrons, or you can have atoms that have almost the same number of electrons. And they're going to interact differently, because if you have a lot of electrons, then you only need a couple to be stable. And if you don't have very many, it's just as easy to get rid of them instead of trying to pull electrons from other random places. So in the first one, we already did all of these. We did the dots. There's the octet. So here, two different types of bonding that we're going to talk about. First one, ionic. And we'll probably get through ionic and all the variations in ionic tonight, and then we'll do covalent next week. Okay? So ionic, this is when a metal and a non-metal combine. This happens because metals like sodium, group 1, they only have one electron. So remember that sodium is element number 11. It has 11 protons and 11 electrons. That one out in that third energy level. If it can lose that electron, how many electrons will it have then? It'll only have 10. If it has 10, what is 10? 10 is, not nickel, neon, right? So 10 would give it a structure like a noble gas. So if sodium with atomic number 11 has 11 electrons, it's got this extra one out in its third energy level. But if it could get rid of that one, then it would have an electron structure like neon, like a noble gas. And so I said that's sort of the goal. The goal is to try and have the noble gas structure. Chlorine, on the other hand, is 17. 17 protons, 17 electrons. In the outer shell, it's got 7. If it gains one, it'll have 18. And 18 makes it like argon. So 18 will also make it like a noble gas. And so because sodium has so few, chlorine has so many, it is easier for them to just transfer electrons than to try and share. Because chlorine would have to share 7 electrons, and sodium just don't have that much to share. Sodium only has 1, so why would the chlorine care? Okay, it's not an equal thing. They're not close to having the same amount. Since one has very few, one has a lot, it is easier to do an electron transfer. So we are just going to actually pull the electron off of the sodium and give it to the chlorine. So if sodium loses its electron, now it still has 11 protons, but now how many electrons does it have? 10. 11 positive charges, only 10 negative charges. That is why they draw it with a positive charge. So it has one more proton than electron when it loses its electron. So the kicker is always to remember electrons are negatively charged. If you lose negative particles, you're going to become positive because you'll have more positives compared to the negatives. If you gain a negative electron, then you're going to become more negative because you're going to have more electrons than protons, which is what happens to the chlorine. So chlorine now has 17 protons and 18 electrons. So that is why you see the chlorine written with the negative charge. So now sodium, this is not a sodium atom. This is not a chlorine atom anymore. When they're atoms, they have equal numbers of protons and electrons. So a neutral atom, like an element, has equal numbers. But in this one now, we have taken the atom and converted it to an ion. So an ion is just an atom with a charge. So it's an atom with an unequal number of protons and electrons. If it has more protons than electrons, it will have a positive charge, and it is called a cation. And although we haven't done very many examples of this, it is always a metal. Okay? Cations are always going to be your metals, with very few exceptions. And you've got the periodic table. How do you know where metals are? Yeah, you look at the zigzag line, right? Everything to the left is a metal. Okay? Except what? Oh, well, yeah, hydrogen is the little ball. Okay, but for the most part, you can say that everything on that side, they all have few numbers of electrons in their valence shell, so it's just easier for them to lose it. The negatively charged ions are called anions. They will have more electrons. They are always going to gain electrons. And they're always the nonmetals. So sodium metal is super reactive, explosively reactive with water. You have to store it underneath kerosene in order to keep it from reacting just with the air. It would automatically oxidize if you put it out, like just set it out. And it would generate a lot of heat. So it would like melt things. So it would end up being a whole, like you'd have a big hole, like it'd burn through all kinds of stuff. And so sodium, it's all that reactivity is all because of that electron. It's like sodium just trying to get rid of its electron just as hard as it can. So sodium atoms become ions as fast as they can. Chlorine, same thing. Chlorine atoms, extremely reactive. Even chlorine gas, very irritating. That exists as Cl2, but it's still a very reactive molecule. It's good for disinfecting water, treating swimming pools. But if you've ever inhaled a good inhale of anything with chlorine in it, takes your breath away. You're like, afterwards, trying to recover from that, very reactive. Same thing. Wanting to gain electrons from wherever it can. But when these two combine, what do you end up with? What is that? It's table salt, okay? You use it all the time, right? You shake it on I put it on my egg this morning. So it's extremely stable because it's been able to do this electron transfer. The metal has been able to lose its electron to the nonmetal, and it creates a very stable compound. So this is sort of a great just sort of general rule that you can say about ionic compounds. Ionic compounds are always between metals and nonmetals. Metals and nonmetals. Metals always will lose their electron. Nonmetals will gain. You can actually tell the charge that the metals and nonmetals will have just from looking at the periodic table. So you said sodium loses its one electron, so sodium, lithium, potassium, they'll always be +1. So the group number tells you the charge too. It tells you the number of valence electrons, but it also tells you the charge. So the first column will have a +1 charge. Second column will be +2. Going over aluminum, all the way over, starting in that third column, aluminum is really the only other metal on that side. So aluminum is in group 3, so it would be a +3. So the metals are always going to lose their valence electrons, so their valence number is equal to their charge. Nonmetals are a little different because like we did with chlorine, we said chlorine has how many? 7, and it's going to gain 1. It's going to gain 1 negative electron, so its charge will be a -1. So the easiest way to remember is you just take their group and take it away from 1. Figure out how many electrons do they need in order to have 8. So if you take 7 minus 8, that's a -1, okay? Nonmetals will always be negatively charged because they're going to gain electrons till they make 8. So you can figure out how many they're going to gain to make that 8 and assign that charge. So we did this with magnesium. We took magnesium, that was the solid, I lit it with oxygen, and we made a magnesium-oxygen combination. They combined because magnesium's a metal and oxygen's a nonmetal. So we made an ionic compound just by burning that strip of magnesium metal. So what's the charge on that magnesium? Because your periodic table, it would be +2. Okay, so magnesium's in the second column, so it'd be a +2. Metals are always going to be the positive charge based on their group number. What about the oxygen? It's going to be a It's in group what? Group 6. So remember, the number in front of the A tells you the valence number. So it's got 6 electrons. So to make 8, it's going to gain 2. So it's a -2. So that means that 2 electrons from magnesium get transferred over to the oxygen. Do you notice that it looks like it's even? Like the magnesium's a +2, the oxygen's a -2? So in that, you can figure out what the formula is as long as you know the charges. So they call this the swap. So the charge on the metal tells you the number of non-metal atoms. So this 2 tells me that there's a 2 here. This 2 tells me that there'd be a 2 here. So you take the charge and swap them, and it actually tells you the ratio that the atoms will react in. The only difference with this one is you always want to have the simplest ratio. So if Mg2O2, what would I do? If I needed to simplify, 2 and 2, just make those both what? You would just simplify. So if you had 2 and 2, you would simplify it to a 1 and 1. That's the simplest ratio. So that's what we made. So that ashy stuff that's in the petri dish or in the watch glass now, so it definitely looks different, right, than that strip looked. So it's this white ash that's left behind. So it looks different. So if I like mash on it, I can like break it all up. So it's just this white ash that's left. This is magnesium oxide. So the magnesium oxide reacts. The magnesium reacted with the oxygen when I put the flame to it, gave off that really bright light, but now I've made this really stable ionic compound. And the simplest ratio is that I had 1 magnesium per 1 oxygen combined. And the formula is MgO. Just like sodium and chlorine, 1 and 1, when you swap them, that tells you the ratio that they exist in. 1 sodium to 1 chlorine, a positive and a negative charge. Last thing you can do is you can name these and use sodium chloride as your guide. So if you say, okay, NaCl sodium chloride, so what would MgO be? Magnesium oxide. Sorry, MgO. So the first word is always what? It's always the same as the first element. So you always use the whole name of the first element. It doesn't matter what it is. It's always the metal, but you always use the whole name. The whole name of the first element, which is your metal. And then the second name is what? Kind of like the first syllable. First syllable of the second element plus IDE. So all ionic compounds have that, how you create formulas and how you would say names. Follow exact same rules. So let's look at some of the ones that are here. Where is it? Right here. So in this one, so if you had lithium, you just call it lithium. If you had sodium, you would just call it sodium in the name. Notice that potassium +1, you just say potassium. Mg +2, you just say magnesium. Calcium +2. And strontium, barium, I won't do very much. There's aluminum over there. Those are really the ones that are the more familiar, the ones that you'll see more are those first 2 columns, the first 1 through 20, and then aluminum over there. But then looking over at the 8 that are over in the yellow side, those are the nonmetals. So when you have nitrogen or phosphorus, see it's in group 5A, which means it's going to have to gain 3 electrons in order to have 8. That's why they have a -3 charge. Oxygen and sulfur, they're going to have to gain 2. They're in group 6A. They have to gain 2 electrons in order to be stable. That's why they end up with a -2 charge. Fluorine, chlorine, bromine, and iodine, they have 7, which is why they end up with a -1 charge. That makes sense?
Yeah. Why isn't carbon and silicium?
Well, carbon has 4, so then when you start getting to carbon, you can make like some ionic compounds.
It's relatively stable at that point.
No, it's because carbon only has 4. And so 8 is stability, and it has 4. It would much rather share.
Oh, okay. So
Okay. So because the other nonmetals have almost 8, like 5, 6, 7, that's why they're going to do this transfer with metals that have very few.
So the carbon and the other one are going to do not the ionic, but the covalent.
Yeah.
bonding.
Much more common.
Okay.
So, pretty easy naming the metals. You just use the whole name. But now, what are you going to call something that ends with a nitrogen? So nitrogen will become nitride. So what will phosphorus become? First syllable. Oxygen, we said, is the oxide. Sulfur, sulfide. Fluorine is like when they talk about brushing your teeth with fluoride toothpaste. And now that one is, remember you put UOR, otherwise it's flour. Okay, that's one that like people constantly like misspell. So chlorine you're familiar with. Bromine is, and iodine is iodide. That one I'll write. So we're just going to make combinations of these, because if you know based on the group what the charge on the metal is, and you know based on the group what the charge on the non-metal will be, you can just do any combination of metal and non-metal, figure out a formula, and give it a name. So let's do that. We did the first one, and we did the second one. So CaCl2. So calcium, when you look at it, remember calcium's a +2 because it's in group 2. Each chlorine is a negative, and there's 2 of them. So notice the charge tells you the formula. The charge on the calcium tells you there has to be 2 chlorines. The charge on the chlorine tells you there's only 1 calcium. So I call that the swap. Swap the charges in order to tell you what the formula ratio is. And then the name? Calcium chloride. K3N, find potassium. Its charge is what? +1. And the nitrogen is the -3. Notice that you swap the charges again. The charge on the potassium tells you there's 1 nitrogen. The charge on the nitrogen tells you there's 3 potassium. So that's how you work out the formula that you would have potassium to nitrogen. So if it's a plus, it's a +1. So that 1 tells you there's only 1 of those nitrogens. This -3 tells you that there would be 3 potassiums. You call this potassium nitride. So I could give you the formula and you could tell me the name, or I could give you the name and you can work out the formula. So I did that here. So this is actually a new slide. You'll have to add these ones in. Just add them in as we go. Kind of put them in there somewhere. So in the first one, you just want to write out the name of those 4. And then for the second 4, I want you to work out what the right formula would be. So I tried to use all the metals and all the non-metals that we have to know so that we would have a chance of going over examples with each one. Okay, so I just wrote the rules up. Whole name of the first element, first part of the second element, plus IDE. Normal, common, ionic compound, so this one is magnesium chloride. K2S would be potassium sulfide. that's not a T there. BEF. Beryllium. That's a Y. YLLIUM. Beryllium fluoride. Li2P. Lithium phosphide. Good. Okay, so just sort of same rules apply. If you're given a name, you can work out the formula. So I wrote the instructions on the bottom. So you're going to write each element and their charge. Remember that the metal is always going to be a positive charge. Non-metal is always going to be a negative. Metals, its charge is from its group, its valence number. Non-metals, it's how many from 8 in order to make it. And then once you get that done, you do the swap. So I put X with a plus A, Y with a minus B. So you would take A and B and you would swap them, and that tells you the ratio. The only thing to do is if you can, simplify. So if you came out with 2 and 2 or 3 and 3, you would want to simplify that. Okay, so it's the simplest whole number ratio. So maybe add that in there too. Not simply. That's how you spell it. Just make sure you go back and simplify if you can. So sodium is a plus. Write the symbol and the charge. Bromine is a Br with the minus. So you have +1 and -1. So yeah, it would just be NaBr. So it's a 1 and 1. Calcium oxide. So Ca is +2. And you could put +2 or 2+. I don't care. Okay? Like you'll notice in your book, I think they put 2+ all the time. I just don't. I don't know why. I always put my charge and then the number after. It's just me. It doesn't matter one way or the other. Either one's fine. But then the oxygen is 2 negative, -2. Either one.
Okay. So to get to, you subtracted the proton.
Nope. The group number at the top. 6A. See group 6A? It's 8 minus 6 is, okay? So it's always the group number. So same thing when you're figuring out the charge for calcium, you're going to use the group number at the very top. Group 2A tells you it's a +2. Charge on oxygen, group 6A, so 6A, 6 minus 8 or 8 minus 6, whatever. You know that that non-metal is going to be negatively charged. So now what do? So if you swapped, it'd be Ca2O2, and then simplify. So this one would just be CaO. Aluminum nitride. Aluminum Al is, nitrogen is, you see that one? Nitrogen's in group 5A, so 8 minus 5 is 3. That tells you the charge on the nitrogen. Swap them, and you're going to get Al3N.
I'm sorry. No. Because that number above is 7.
Not the number not the atomic number. It's called the group number. So do you see above nitrogen, see the number 5A? That tells you the number of electrons in the outer shell. That's the valence number. So the number in front of the capital A. So if you look, so helium and all the ones in column 1 are 1A. That means that they all have 1 electron in their outer shell. It doesn't matter which one you're talking about. All of them have 1. Second group, all of them have 2. When you get over to aluminum, they're in group 3A at the very top, +3. That's why aluminum's a +3.
So why is nitrogen a
Okay, so once you get into the non-metals gain electrons. So that's how many electrons they need to make 8. So 5, to get 8, you have to have 3 more. So that's why it's a -3. Okay? Always the same though. It's like not any more complicated, I swear. Well, there's a few things, huh?
It looks like it.
I know, it looks like it should be terrible. Like this should be really hard. Why is this so easy? Okay, so Al3N3, then just make sure you go back and simplify. And yeah, ALN. Okay, always simplify if you can. So, magnesium iodide. Magnesium is Mg plus 2. Iodide is I negative. So just take the charge and swap them. So Mg, there's only one of those because iodine is a -1. So you can remember it's a negative or a -1. Doesn't matter to me. If you just see just a negative, that means a 1. And then I would be 2. Charge on the metal tells you the number of nonmetals and vice versa. Can I simplify this though? No. Okay. So it's just MgI2. So it stays as is. People are like, that's not terrible. Okay, better? Okay, now remember on this next exam, you're going to get another card. Okay, you'll have another note card. Those might be good things to put on your note card with maybe an example. Okay, so that as you start, and you may want to start like a page of like stuff to go on the note card page. So after we cover lecture, maybe go back over and be like, yeah, I better put that on the note card. So then when it comes time to fill out the note card, you've already got your list of stuff that you want to make sure that you could refer back to if necessary. Okay? So, go ahead.
Okay, so let me get this straight. So, everything above 3A, you have electrons.
Everything above 3A has 3 valence electrons.
Okay.
That is electrons in the outer shell. Okay? They have more than just 3 electrons, but the other ones are on the lower levels and they're already full. So they're already stable. They're not going to interact. They're not going to cause trouble for the most part. There's some weird expanded octets and all kinds of stuff like that, but we're not going to talk about those. We don't need to be doing all that. So, the oddballs. There's 2 examples of oddballs in ionic bonding, and I'm going to put a box around the 3 that I want you to recognize. Chromium, iron, and copper. These are 3 that you actually had in your list of symbols and elements to know. So Cr, Fe, and Cu, chromium, iron, and copper. Notice those ones in the main group, the ones on the 2 on the left and the 6 columns on the right, they're all nice and even looking. But these ones in this middle group, they call them the transition metals. They call them this because they can go through transitions. So they can actually have more than one possible charge. So they found that some chromium atoms will lose 2 electrons and become stable. Other chromium atoms will actually lose 3 electrons and become stable. So they can exist in more than one way. So we can have Cr plus 2, like that would be CrO. Right? So the chromium, if chromium's a plus 2, oxygen's a minus 2, do you see how they would be like a 1-to-1 ratio? So we could have just CrO, call it chromium oxide. Problem comes into play is if it's a chromium plus 3 and O with the minus 2, now when I swap, what's my formula? So notice the charge swaps to form the formula. So see, they exist in 2 different forms. I can have CrO or Cr2O3. So how would I know which one is which, other than the formula, like when I name this? So when I name this, I have to tell you which chromium I'm talking about. This is where the Roman numerals come in. So if it's this first one, I would call this chromium 2 oxide. I use a Roman numeral. The Roman numeral 2 tells me it's the plus 2 chromium. So if it's the other one, I would call that one chromium 3. And that's how I can tell them apart. So they used to do like chromous and chromic oxide, which are like Latin terms. And people were like, nobody likes that. And so then they've finally gone to this. This is the more like modern or consistent form. If you have a metal that can lose more than just one type or number of electrons, then you use a Roman numeral to indicate the charge on the metal. That's what this tells you. This tells you that it's chromium plus 3. So the Roman numeral 3 tells you the charge. It doesn't tell you how many chromium. It doesn't tell you the number of chromium. And that's sometimes a mistake that I see is people want to say, oh, well, Cr3, it'd be chromium 3 oxide would be Cr3O because of the 3. That's not what that tells you. Okay, the Roman numeral tells you the charge on the chromium so that you could work out the formula. So the top one's chromium 2 oxide, bottom chromium 3 oxide. Iron does this too. So you can have FeCl3 and you can have FeCl2. So both of those, what would I call them? Just their general name would be Fe is iron, Cl would be chloride. So they're both iron chloride, but because they're one of those transition types, I would have to call the top one, I have 3 chlorines, what's the charge on that iron? Right, well, you know the chlorine, right? So chlorine's given, so you know the chlorine's a negative. And if there's 3 of them, that means what does the charge on the iron have to be? Plus 3. So do you see it's almost like a reverse swap? So you can take those, you can take the formula and use it to figure out what that charge is. So 1 iron, because 1 negative charge on the chlorine, the 3 chlorines tells me that it's a plus 3. What about this one? So this one, if it's still, chlorine's always negative. So there's 2 of them, so the charge on the iron would have to be plus 2. The positive and the negative charges total have to balance. So the total number of atoms and positive charge on the metals have to equal the total number of charges and the number of nonmetals. So this one, the top one, you would call iron what? 3 chloride. Bottom one would be iron 2 chloride. Just put yourself a note. These are the 3. And we'll talk about these 3 because we'll actually come back. We're going to talk about copper again when we're talking about carbohydrates. We're going to talk about iron again when we talk about hemoglobin. And so that's the reason to cover these ones and show you that they actually do have this variation ability, the ability to lose varying numbers of electrons and still form a stable compound. Cu3n, Cu3n2. Yes? Oh, it's right. Yeah. It's like, what do you think? So before you can name this, you got to figure out what the charge on the copper is. And you can figure out the charge on the copper because you know the charge of the nitrogen. So you know the nitrogen is, right? So nitrogen's always going to have that -3. So this one, it's like you know the charge on the nonmetal, so you can figure out the charge for the metal. So in the first one, what do you think the charge is? Can you see that the number swapped backwards tells you the charge? 3 copper, -3 on the nitrogen, 1 on the nitrogen, plus 1 on the copper. What about the second one? The number on the nitrogen tells you the charge on the copper. The number on the copper tells you the charge on the nitrogen. So now I can name this. So Cu is copper 1 nitride. This one is copper 2 nitride. These are the only 3 ones that I'll use. I'll use chromium, I'll use iron, and I'll use copper. Okay? So you do notice there's a couple other ones, but we just really don't talk about them as much in terms of their structure or their use in the body, but we will talk about these other ones, so that's why I just include these 3. So again, maybe something that you want to make sure you put on your, be sure to put in the note card list, okay? Continue, just start building that list because that'll help, because these are kind of like little nitty-gritty rules. But if you have them, down, then you've got those to refer to. Okay? There's one more. Just hold your breath. That is the polyatomics. There's one more set of ions that exist as a group. So it is a group of nonmetals that collectively have a charge. A group of nonmetals that collectively have a charge. It's almost always nonmetals with a bunch of oxygens. Sometimes they have 2 oxygens, sometimes they have 3 oxygens, sometimes they have 4. But they have these oxygens surrounding them, and they gain electrons and end up with a charge, typically negative charge. The only positive one is the NH4. Polyatomic ions that we have to know, there's more than this, but the ones we're going to stick to are pretty much the ones that end in ATE, not IDE. And when you do their naming, you use the name of the polyatomic. So there is a chart in your book. Here's the chart. The boxed ones are the ones you need to know. The only ones I'm going to add are the top 2. I don't know why they didn't box them, because those are ones that we talk about, the hydroxides and the ammonium, we actually talk about on a regular basis. So we add those. So that means that you've got 7 of them. So OH minus. That means that it's an oxygen and a hydrogen, and together has a negative charge. They call it the hydroxide. Sodium hydroxide. We've used that in class, right? In lab, the very first week, you put sodium hydroxide on the egg, and the egg got all mushy. Okay, so I told you it's kind of like lye, or kind of like Drano in terms of its reactivity. That's the hydroxide ion. Bases create hydroxide ions, so that's to be familiar with that one's a good one. We'll go through the other negative ones. We have NO3 minus, that is the nitrate. And it's always written out as that together. ClO3 minus, that is the chlorate. CO3, that's a 2 minus. It has to gain 2 electrons to become this stable polyatomic ion, and that is the carbonate. You may have heard of this one, which is HCO3 minus. That is the bicarbonate ion. So it is very similar to the carbonate, just has an extra hydrogen on there. SO4, 2 minus. The sulfate. So you know it's always kind of like the term of the nonmetal with all those oxygens, that ATE on the end. And then the last one is the phosphate, PO4. And that one's a 3 minus. So all of these react with metals to form ionic compounds. And you would name them. You always use the whole name of the first substance, right? So that would be sodium. And then you just use the name of the polyatomic. So this is where the name and the formula, the charge becomes important. So that ClO3, this would just be sodium chlorate. So K3PO4. Whole name of the metal, and then just the name of the polyatomic. So potassium phosphate. So what would calcium sulfate, what would its formula be? So you look at calcium, so you're like, okay, well, calcium Ca, and you know the charge on calcium would be +2. And then you look at the sulfate, so that one is SO4 2 minus, so plus 2 minus 2, so what happens? They're already balanced, so you're going to simplify that ratio, so it would just be the simplest ratio. We'll do more of these. We'll go back and do a little more transition practicing on Monday when we come back together. In the meantime, you can go ahead and do the ionic compounds dynamic study module, because we've really finished all the ionic compound information. Okay, so doing that in the next couple of days, that'll like help to try and reinforce, picking out metals and non-metals and putting them together, figuring out formulas and naming. Because we've really covered everything that's related to ionic compounds. So we'll do some practice of this, and then Monday we're going to do covalent, okay? And hopefully finish up chapter 3 by Wednesday.